hello. Welcome to the midterm one review session. Today I plan on going over like the practice midterm one here. Um, there is one question that has two answers, which is the one with the three-membered ring. This one here has two answers, right? And we'll go over the predicted product, mechanism, the explanation questions, and synthesis problems. But before that, do you guys have any questions or topics you guys want to go over before I go over this practice midterm? Okay, it's good. So let's go over the multiple choice here. This first question is asking us to find like which reaction forms both the syn and anti-products. And there is, let me actually pull out like a cheat sheet that I made for Helix 118B class a while ago. So let me pull it out here for you guys. Okay, let's see here. Exam one, midterm one, this one. Okay. Send the copy. Okay. Yes. So here's a table of the 118B midterm 1 alkene reactions and the reagents that you need to know with the regioselectivity and stereoselectivity, like whether it's Markovnikov versus anti-Markovnikov, none. If you see none here, then that means that it doesn't matter, because in hydrogenation, for example, we're adding two hydrogens across the double bond. So we're adding hydrogens on both the more sub side, Markovnikov side, and less sub side, anti-Mark side. Right. Same as for halogenation with X2 and a product of it, CCl4. Right. But halogenation in products of it, like with water or alcohol, will be Markovnikov addition, because we're adding water or alcohol on the more sub side, right? Because that nucleophilic solvent, the product solvent, attacks the more sub side. Like it attacks the more sub side of the halonium ring, like a bromonium ring or chloronium ring. Right. When you see none for syn addition here, think of that as both syn or anti addition, right? Because of the carbocation intermediate or radical intermediate, right? So when the nucleophile comes into attack, it could attack on the top side, giving you a wedge product, or the back side, giving you a dash product, right? So when you see none, think of that as both for Helix's class, right? Okay. Before I moved on to like the iPad cheat sheet, this is like the cheat sheet I made on paper, where this is like the front side of the cheat sheet. This is the back side of the cheat sheet. It's separated by all the reactions and mechanisms you need to know, and whether or not it's like syn addition, anti-addition, Markovnikov addition, anti-Mark addition. There. Okay. Okay. So let's go over. Yeah, we could go over mass spec as well. Like I have mass spec notes here with Helix's annotated slides, and it's multiple choice questions as well. Right. Okay. So first question, which reaction forms both the syn and anti products? Do you guys have an idea of what this would be? Like what the answer here? So, A, B, C, D. So we could go down each one. Hydroburst oxidation, that would be syn addition. Yep. Radical addition of HBr, right? That's the one with HBr, roar, and heat, right? Because this reaction here goes through a radical mechanism, and that radical is going to be sp2 flat and planar. And because of that flat and planar geometry, it could either be wedge or dash, right? Giving us syn or anti-product. So it's going to be B. Hydrogenation, syn addition, halogenation, anti-addition. Okay. Next question. Which of the following reactions involves a single step mechanism? So this one here, Helix didn't go over the mechanism as much. I think, right? Did he go over epoxidation with MCPBA mechanism in class with you guys? Yes. Okay. Yeah. So you guys are going to notice that this mechanism here is going to be one step, right? But that one step has a lot of arrows happening simultaneously at the same time, right? A lot of migration steps. So the answer here is going to be B. Hydroversion oxidation, there's like two steps. The hydroversion step and then the oxidation step. Radical polymerization, there's like either a cationic polymerization or radical polymerization. For the radical one, there's like initiation, propagation, termination. So there's multiple steps there. Hydrohalogenation, there's like a carbocation intermediate. So that's multiple steps as well. Okay, next one. Which reaction likely involves a carbocation rearrangement? So this one here, like you guys have to like be familiar with the mechanisms of each reaction. Hydroversion oxidation will not form a carbocation intermediate. An acid catalyzed hydration of alkene, that's going to be the reagents H2SO4 and either water, H2O, or alcohol, ROH. Whenever you see a strong acid like that, H2SO4, with an alkene, that's going to protonate the alkene, forming a carbocation intermediate. And whenever you form a carbocation intermediate, you always stop and look out for any carbocation rearrangement steps, like either a hydrate shift or methyl shift. So right now, B looks promising. C, dihydroxylation with OSO4, no carbocation intermediate gets formed. Halogenation, no carbocation intermediate gets formed, right? Because the intermediate for halogenation is a bromonium ion if you use Br2, or chloronium ion if you use CO2. Right. Okay. So next one, which molecule has the largest heat of hydrogenation? This question here is which one has the highest energy, aka the least stable alkene, right? Which is the highest energy alkene? That's the least stable alkene. And alkene stability is similar to carbocation stability. It's by substitution, right? The more substituted the alkene is, the more stable it's going to be. So these are the different alkenes you could have, like this, right? Where this is an unsubstituted alkene right here. There's no alkyl groups attached to this alkene. This is a mono substituted alkene because there's one substituent, one alkyl substituent attached to that alkene. These three alkenes right here, they're all di-substituted alkene, right? But this one here is a geminal alkene. This one is a cis alkene, and this is a trans alkene, where the trans alkene is more stable than both the geminal and cis alkene, right? The geminal and cis alkene are less stable than the trans alkene because of steric hindrance. These alkyl groups here are bumping into each other. They're close to each other, bumping into each other, causing steric hindrance, which is not good. We don't want steric hindrance. That's less stable, right? And then we have a tri-substituted alkene here, and then a tetra-substituted alkene right here. So the more substituted the alkene is, the more stable it's going to be. So these arrows here that I'm putting in green are the arrows talking about stability, right? Not about energy, because energy would be the reverse of that, because stability and energy are inversely related. Stability, right? If we were talking about energy, it would be the reverse. Like if I draw the arrows in pink right here, these would be the arrows in for energy, where the unsubstituted alkene has the highest energy since it's the least stable. Right? Stability and energy are inversely related. Okay. So let's go back to that question. Let's draw out these molecules here. Ethene, that's 2 carbon alkene, 1 butene, that's that right there, 2 butene, that's that, 2 methylpropene, that's gonna be this right here. So let's analyze each alkene. The first alkene is unsubstituted. There's no alkyl substituent. this alkene here is mono substituent. There's one substituent there. This is di substituent, and this is also di substituent. The least stable one is the ethene one because it has no substituents. And because it's the least stable one, it has the highest energy, largest heat of hydrogenation. Right. Okay. Now, if you were comparing between C and D, which one would you guys say is, let's say, more stable? C or D? Which one is more stable? Yes, C, because it is trans alkene. So be careful of what the question asks for. If the question asks for stability, then look for the more substituted one. Or if they're di-substituted, go for the trans one or the E alkene. If they ask for the heat of hydrogenation, aka energy, then you look for the least stable alkene if they ask for the one with the largest heat of hydrogenation. If they ask for the one with the smallest heat of hydrogenation, like the one with the least energy, then you look for the most stable alkene, right? Because that could be a question as well. So let's say that C is the most stable alkene here. This would be the alkene that has the least heat of hydrogenation. So if the question was flipped, the answer would be C, if they were asking for the least heat of hydrogenation. Yes, there is a PDF of this. Let me download this for you guys. Oh, and also I think this document here as well has like the winter 2023 practice exams for you guys for extra Helix practice. So let me send that to you guys here. Download this one and this one. Okay. So file. Okay. The one I'm going over right now is this file. The one that we'll go over with the extra Helix official midterms from winter 2023 with the note card and table of reactions is going to be this one. Yeah. Okay. Yep. Okay. So the next question is asking for which statement explains why alkenes undergo electrophilic addition reactions. When, let's say, for example, you have this alkene right here, and we do an electrophilic addition reaction, that alkene is going to go away, and we're going to form two new sigma bonds here to some random group, whatever that group is. It could be hydrogen, halogen, alcohol, OR, right? We're breaking that one pi bond to exchange for two sigma bonds. And a sigma bond is going to be the direct overlap of two s orbitals, whereas a pi bond is going to be the parallel overlap between two p orbitals. And because of this direct overlap between two s orbitals here, that sigma bond is stronger than this pi bond right here, right? Because they're not directly overlapping with each other. So when we do electrophilic addition reactions, we're going to make the more stable molecule with stronger bonds here, with more sigma bonds. Right, so let's look at the answer choices here. Alkenes are stabilized by hyperconjugation. That does not explain why alkenes undergo electrophilic addition reaction. That's going to explain why more substituted alkenes are more stable. B, the pi bond of alkenes is weaker and more reactive than a sigma bond. Yeah, so it will be more reactive than a sigma bond because since the alkene bond is weaker, it's going to be less stable. And if it's less stable, it's going to be more reactive than the sigma bond. So that's good. Okay, so alkenes are nucleophiles due to their planar structure. So they are nucleophiles, but it's not because of their planar structure, right? They are nucleophiles because of their double bond right here. This bond right here has 2 electrons, which can be used to attack an electrophile, right? This second part is not good. Alkenes have lower heat of hydrogenation than alkynes. So that right here is not true as well, because alkynes will have more bonds, more to release heat when we do hydrogenation. So the answer here would be B. Next question. Which of the following reactions is stereospecific for syn addition? We kind of went over this in the first question already. It's going to be hydroburst oxidation. This one here is anti. This one here is also anti addition. And this one here is both syn and anti. Okay. Which of the following reactions involves a formation of a 3-membered ring intermediate? So this one here is the one that has 2 correct answers, right? It's going to be oxymercuration, demercuration, and bromination and CCl4, right? The oxymercuration, demercuration goes through this mercuric ion ring, where that's OAC, and the bromination goes to this bromonium ion ring here, where we have a bromine in the middle with a positive charge, like that, right? Radical polymerization, that goes to a radical intermediate, so that's not it. The hydroburst oxidation, that does not go through a 3-membered ring. It goes through like a very long mechanism, which we don't have to like worry about the second part, but you do need to know like the first part of hydroburst oxidation. But I don't think it's gonna show up in the mechanism as much. Like there's less yield, low yield for this mechanism there. Okay, next question. Which of the following results in an anti-Markovnikov addition, where we add to the left subside, right? Radical addition of HBr, that's the one with the roar. That's going to be the answer there. Hydration, that's Markovnikov. Oxymercuration, demercuration, Markovnikov. Hydrohalogenation, Markovnikov. Okay. Any questions on this multiple choice section of this practice? Okay. Yes. Okay. Let's go on to predicted product. Let's also do the mechanism just for extra practice here. Number 1, we have this alkene reacting with Br2 CCl4. So I'm just going to go through this, walk through this. Stop me on the chat or like in the mic when you guys have a question. We have Br2 here and A product solvent, CCl4. This A product solvent here would not interfere with the mechanism. It's not going to do anything in the mechanism, so we could ignore that. I'm going to draw out the Br2 like this. Br, bond out to another Br. This alkene here, we said was nucleophilic. We're going to attack one bromine, kick off the other bromine at the same time as a good leaving group. As this bromine here is gaining electrons, it's becoming more negatively charged, becoming the nucleophile. As this alkene here is losing electrons, it's going to become less negatively charged, more positively charged. It's going to be the electrophile. So because of that, the bromine being attacked is going to attack the other carbon of the alkene at the same time, right? So all these 3 arrows here happen simultaneously, right? And because they're happening simultaneously, we're going to form this bromonium ion ring where it's going to be on the same face. It could either be both wedges like this, like I just drew out, or both dashes, right? Where they're syn to each other on the same side. Question A, the answer was A, right? Anti-Mark addition, radical addition with HBr roar. When you see this peroxide right here, roar, which is this peroxide bond right here, always associate that with anti-Mark reaction, right? Another anti-Mark reaction that you see is going to be hydroburst oxidation. That's because the reagents for hydroburst oxidation is, the first step is BH3, second step THF, second step is going to be H2O2, NaOH, water. This H2O2 right here, if I draw that out like this, we also see that there is a peroxide bond here leading to an anti-Mark reaction. So there's 2 anti-Mark reactions for this midterm: the HBr with roar and heat, and the hydroburst oxidation reaction, right? What other thing can react with roar, right? Besides HBr? Right. Can HCl or HI do anti-mark with roar as well? No, it cannot. Right. hmm But there is something else that can do anti-mark with roar, which is gonna be the one with sulfur. Yes, sulfur. And that could either be H2S or HSR. Right. So if you see something like this, and you see HCl, roar, heat, do not draw this, oh shoot, as the answer. Right, that's not the right answer. Because this is HCl, which would not do anti-mark. It would still follow with the Markovnikov addition, like that. Okay. But if you see something like this, where you have some random R group, let's say like the cyclohexane SH with roar and heat, then you can do anti-mark where you add the sulfur atom to the less subcarbon, right? If I highlighted this sulfur group here with that R group, that's this sulfur group here with that R group right there, right? And if I highlight this alkene in pink like that, that's that pink alkene right there, making this the new bond between the alkene and the SR. Okay. So let's go way back here. Okay. So when we form this bromonium ion ring right here, this dash methyl stays as a dash methyl because this carbon stays untouched. Nothing touches that carbon. If I made this bromonium ion a wedge, this methyl group right here is forced to become a dash, like that. Right. Now, once we have that, the Br minus that got kicked out is going to be our nucleophile. There's no other competing nucleophile. There's no water. There's no alcohol. So we don't have to worry about that yet. Right. We have CCl4 here, which is an aprotic solvent that would not interfere with the reaction. So this Br minus here can attack either carbon of the bromonium ion ring. Let's say we attack this carbon right here and kick off the bromonium ion ring that way, right? This does a backside attack, so it's going to invert the stereochemistry. We're going to invert the stereochemistry that we kicked off, which is going to invert that wedge bond into a dash bond like that, which forces this methyl group to convert into dash bond, right? Now, this carbon here, you could imagine it staying as a wedge bond, right? You could draw it like that to clearly show the anti-addition of this reaction, right? This is anti-addition because one bromine here is wedge, the other bromine here is dash. So that's the anti-addition part of it. But because this is not a chiral center, there's two hydrogens here, right? Not a chiral center. You don't have to put wedges or dashes. You could just like draw this as a flat bond, and that is still correct. But keep in mind that this reaction here is anti-addition because this carbon here, nothing touches that carbon. So if this were to be a chiral center, this bond would stay as a wedge, like that, showing the anti-addition part of this reaction. Okay. And can we do plus minus here in the product or no? Can we say plus in the enantiomer? No, we cannot, right? Because plus minus shows a 1-to-1 mix of enantiomers, and back in 1-A, we said enantiomers are when all chiral centers in the molecule change or flip, right? We see that this chiral center here would flip, but this chiral center here stays unchanged. So the other product, if I were to draw that out, would be like this. We flip that chiral center. This dash methyl here stays the same. Making these diastereomers of each other, not enantiomers of each other, right? So we cannot do plus minus like that. Okay. Any questions on this question mechanism? Can you draw both of them and then write plus minus for each? Yes, so that's what Helix does for his exams. but I'm trying to figure out like why this one not. Yeah. If you draw the both out, you could do plus minus for both, and that would still work. Yeah. Okay. Number 2, when you see MCPBA, think of that as peroxide bond with carboxylic acid, which is going to create an epoxide from an alkene on the same side. So we're just going to create an epoxide like that, forcing this methyl to become a dash. And because these are the only correspondence we have that will change, we could do plus minus here. I just chose to draw as a wedge because it looks neater that way, but this epoxide here could have been a dash as well, forcing this methyl to become a wedge like that. Okay. Now, HBr and ROR, this is going to go back to the initiation, propagation, termination steps back in 1A when you guys learned about free radical halogenation. We know that this is going to be an anti-mark reaction. So let's add bromine to the less subcarbon right away, like that. Here's the mechanism. Initiation, I'm going to draw out the peroxide bond like this. The bond here has 2 electrons. One electron is going to go to one OR radical. The other electron is going to go to the other OR radical to create 2 OR radicals right there. One OR radical is going to react with the HBr, forming an ROH bond and creating a bromine radical bond like that. And this bromine radical here is the one that we are trying to get in the initiation step. For propagation, let's bring in that bromine radical that we just formed and this alkene that we have here in the reactant. Now think of radical stability as carbocation stability, right? The more substituted the radical is, the more stable it's going to be. So from this alkene here, we want the radical to be on this more sub carbon right there. To do that, we have to react the Br radical with the less subcarbon right here. Right, so we're going to attach the bromine to that less subcarbon to allow for us to form the more stable radical at the more sub position right there. Right, that's why this reaction here is anti-mark addition. We add the bromine at the less subcarbon to allow for this more stable, more substituted radical intermediate. Right, okay. Now, let's use that radical intermediate we just formed and bring in another equivalent of HBr because we have excess amount of that. We're just going to quench that radical by reacting with HBr to make it neutral and form another Br radical, which is why this is a propagation step, right? We are forming more radicals, propagating the radical chain. And that gives us our final major product here. And for termination, Helix doesn't really care about that step. But if he asks for the mechanism for this, I will draw at least one termination step. There's a bunch of termination combinations you could do where you just bring in any 2 radicals together to stop the radical chain, right? To make it neutral. So that's one combination right there. Another combination, which would be easy, is just like to bring in 2 Br radicals to form Br2, right? But that's a side product. Like these 2 here are side products right there, right? So any one termination reaction would work for Helix's class in the mechanism. Okay. Number 4, osmonium tetroxide. Okay, so this one here is going to create a vicinal diol, 2 alcohols that are vicinal to each other, adjacent to each other. And when you see osmium tetroxide, that's a big sign of syn addition. So we're going to add alcohol on both carbons of the alkene on the same side. Let's choose wedge here. It could be dash as well. But if I chose wedge, this methyl group here is forced to become a dash. And since these are the only 2 correspondences that are changing, we could do plus minus right there. Okay. So, number 5. When we have an alkene right here with a strong acid, H2SO4, that strong acid is going to protonate the alkene. But there's 2 carbons that we could protonate. We could protonate either this carbon or that carbon right there. We want to be able to form the more stable carbocation. We want to make the carbocation at this more stable position right there. So that means that this less subcarbon here is going to attack the hydrogen, be protonated, to form the more substituted carbocation right here. Right. But whenever you form a carbocation intermediate, you always stop and look out for a rearrangement step, like either a hydride shift or methyl shift. Right. In this case, we have a secondary carbocation. To the left, we have a tertiary position. So I'm going to explicitly draw out that invisible hydrogen out and shift that bond with the hydrogen over to that carbocation to give us this more stable, more substituted carbocation right there. Right, this hydrogen here that shifted over is right here now, but I'm going to leave it as invisible. This dashed isopropyl here lost its stereochemistry. It's now flat and planar because this carbon is sp2 hybridized now. Now, once we reached our more stable, more substituted carbocation intermediate, we bring in whatever product solvent we have, water or alcohol. In this case, it's alcohol, to attack the carbocation. Specifically, the oxygen atom of the alcohol is going to attack that carbocation. And because this carbocation is flat and planar, the oxygen can approach on the top side, giving us a wedge product like this, forcing the isopropyl group to become a dash, or the other way around. It could have approached on the back side, inverting this. This could have been a dash, and this could have been a wedge. Right, so that's going to be the plus minus part of this. This oxygen here that attacked that carbon right here is attached to a hydrogen. So I'm going to draw that hydrogen out like this, and an R group, where the R group here specifically is methyl, CH3. And the formal charge of this oxygen here with 3 bonds and a pair of electrons is going to be positively charged. The final step of this reaction is to neutralize or deprotonate that oxygen using the HSO4- conjugate base that we formed in the very first step. Grab that hydrogen, the bond between that hydrogen being grabbed and oxygen right there, those 2 electrons are going to go right on that oxygen right there, neutralizing it. Making this neutral OH plus minus like that. And we reformed our acid catalyst H2SO4 as a side product. Right. Okay. Yes, you can deprotonate it with CH3OH instead. Like instead of HSO4-, you can deprotonate it with CH3OH as well. Yeah, it would be OCH3, not OH. Yes, yes, right. OCH3. OR, if you have alcohol as a solvent, right? If you had water as a solvent, H2O, then the product would have OH, like that. Nice. And if you guys recognize here, we just minus one hydrogen to get the final product. Like this ROH minus 1 hydrogen is that OR right there, OCH3. H2O minus 1 hydrogen is OH, like that. And that minus 1 hydrogen here is being deprotonated by either the HSO4- or water or alcohol. Okay. So be careful of this hydride shift right here. That step is probably a commonly overlooked step. Like sometimes people just put the water or alcohol to that carbocation being formed right away without doing the hydride shift, but that's the minor product, right? Don't forget about the rearrangement step if there can be one, right? Okay. Now let's do the next one, number 6. Okay. So number 6 here is going to be the same first steps as the one we did previously. Br, form the bromonium ion ring. Let's make them both wedges. If I make them both wedges, this ethyl group here is forced to become a dash. Bromine with a positive charge. Now, this is different though, because we do not have an A product solvent anymore. We have a product solvent which is nucleophilic. There's a competition of nucleophiles now. We could either use the Br- or the ethanol. at first glance, Br minus looks like the stronger nucleophile because it has that full negative charge right there. Whereas this alcohol here is just neutral. There's no full negative charge, right? But the reason why ethanol or water here is going to be the nucleophile is because there is a lot more excess of that molecule versus this one equivalent of Br minus that we kicked out in the first step, right? So because of the excess amount of this ethanol, that's going to overpower this tiny Br minus right there, right? Another reason you could think about is the electronegativity of these atoms. Bromine is more electronegative than oxygen, so it wants to keep its electrons. It doesn't really want to give it up and attack an electrophile. Whereas oxygen is less electronegative than bromine, so it's more willing to give up its electrons and attack an electrophile, right? Now, if this is our nucleophile here, will it attack the more subcarbon of the bromonium ion ring or the less subcarbon of the bromonium ion ring? Yes, more subcarbon. And instead of memorizing more sub or less sub, do you guys know why we attack the more sub carbon? Right, instead of memorizing it, but yeah, you guys are right. It's gonna be the more subcarbon. But why? This might come up as an explanation question, like why does alcohol or water attack the more sub side of the bromonium ion ring? So this is like acidic conditions because we have this positive charge intermediate here. And it's going to be more about hyperconjugation, right? Because if you think about this as a good leaving group, and let's say we break open the ring this way, forming a carbocation over here. That's a tertiary carbocation. If we break open the ring this way, that's going to form this secondary carbocation right here. The more substituted carbocation is more stable. So at the more sub position, the positive charge is bigger, right? There's more positive charge residing in the more subposition because it's more stable there in acidic conditions. Yes, it's more stable there. Right. The positive charge is more stable here. Only in acidic conditions, right? Only when we have this positively charged intermediate. If we did this in basic conditions where this is neutral, then it's going to be the less subside because of a different reason, right? Because of steric hindrance. So this reaction here in acidic conditions, it has both SN1 and SN2 properties. The SN1 property is that we're going to attack the more subcarbon. The SN2 property is the backside attack, invert stereochemistry. Backside attack. Invert stereochem. Right? So when this alcohol here attacks the more subside, we invert the stereochemistry there when we kick off that ring. Right? So the SN2 part of this reaction is that we attack the more subside. The SN2 part of this reaction is that we invert the stereochemistry. And I'm going to show you guys what it looks like in basic conditions, just in case it shows up. If we do backside attack, that dash methyl ethyl becomes a wedge ethyl. This is the new bond dash to oxygen. This bromine on the other side stays as a wedge because nothing touches that wedge carbon bond. This oxygen here is attached to an ethyl group. Boom, boom. A hydrogen and a positive charge. The last step, we neutralize it with HSO4 minus to reform our acid catalyst H2SO4. To give us this product here. And can we do plus minus for this product? Plus, I mean, in the enantiomer? Can we put this symbol in the product? No, we cannot, right? Because of this pre-existing chiral center here, that does not change. That is going to form this diastereomer instead, where the two carbons that will change are going to form this product here, creating diastereomers, right? And we could do plus minus for both. Plus minus for both. Okay. Next one. Okay. Does someone want to... Can BR be a wedge? Oh wait, this is supposed to be BR here. BR. And then if I flip that, That should be dash. Yeah. Right. We see that this reaction here is anti-addition because the OR is anti to the BR. OR is anti to the BR, anti-addition. Yeah. BR can be a dash. Like, because the reason why is because when this alkene makes the bromonium ion ring, this alkene is flat and planar. So when we make the bromonium ion ring, we could either go on the top side, making a wedge bromonium ring, or the back side, making a dash bromonium ion ring, right? Which leads to this dash bromine here. Yes. You have a question about question 6? Oh, yeah. Of course. Okay. Okay. Does someone want to go over the mechanism for question 7? Someone want to walk me through this? We have an alkene with a strong nucleophilic acid. What's going to happen in the first step? What's going to happen between the alkene and strong nucleophilic acid in the first step? Alkene attack hydrogen, carbocation forms on the secondary carbon. Yes, correct. Strong acid, we want to protonate the alkene. Kick out the bromine minus ion to create a carbocation on the secondary position. That's good. Okay. Once you have this carbocation intermediate, what's going to happen next? Yep. Yes, shift. Br minus does not attack right away. We have to look out for a shift. Hydride shift. So let's draw out that hydrogen out. Shift that hydrogen over there. Lose the stereochemistry of this wedge to flat. And then Br minus comes in and attach just to the tertiary carbon. Correct. Br minus comes in, attack tertiary carbon. And because this is a flat carbocation, the Br can approach on the top side or the back side. If it approaches on the top side, that would form a wedge product forcing this methyl to become a dash. And because this is the only chiral center that can change, we could do plus minus there, giving us this final product, final answer. Nice. Okay. Any questions on this one? Can the hydrogen shift happen across more than one carbon? So it can happen, but it's very rare and it's going to be low yield. So if you have something like this, and let's say you attack that hydrogen, kick out the Br, and you form a carbocation at the secondary position right here, there is a more stable position across, but that's too far away. Like it can shift all the way over there, but it's going to be very low yield. Low yield, too far. Right, so no hydrogen shift there, it's too far. Yeah. Okay. Next one. Ooh, my favorite alkene reaction. How would you guys predict the product for this reaction here? It's my favorite one. Favorite alkene reaction. Oxidative cleavage. Put carbonyls on alkenes. Yep. Scissors. Think of it as cutting this double bond in half, cutting double bond in half, cutting double bond in half, right? Put oxygens in the middle like that to easily predict the product. So that's the cut right there. Put that alkene. Go boom, 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 boom. Like that. Yeah. So we see that that's this cut right here between this alkene. This is this cut right here for this alkene, and that's that cut right there for this alkene. You could leave this as your final answer and still get full credit. You don't have to worry about redrawing it nicely. because that's the same thing, right? As long as like it's clear of where your carbons are, like make sure like your carbons are well, like, you know, bent and drawn out. Don't make them curved or hard to read. Can you show how much of the mechanism we need to know for this? Yes, so for ozone analysis, I think Helix posted a study guide for how much he wants you guys to know. Let me see how much he wanted you guys to know here. Let's see. Ozone analysis. Up until the ozonide, not until the reductive step. Okay. Yeah, the mechanism for up until ozonide is still pretty tricky because of the migration step. But I could show it to you guys anyway. Here, it's gonna be very weird to follow along, but let's do it. Okay. If it said one equivalent, can we choose any double bond or is there an order? If it says one equivalent and you would selectively go for one, I would go for the more substituted alkene, right? Because if you have this alkene, like polyalkene right here, where there's multiple alkenes, and you only have one equivalent of MCPBA, do you guys know which alkene would react with the MCPBA? Would it be this tri-substituted alkene, or would it be this mono-substituted alkene? More subalkene, right? The more subalkene here is gonna react with the MCPBA, the more stable one. Yes, right. So if it says one equivalent of ozonolysis, I would go for the more stable alkene just like that. But I don't think that you're gonna get one equivalent of ozonolysis. When you have multiple alkenes, you would cut all alkenes, right? I haven't seen an example where it only cuts one alkene for ozonolysis, but I have seen an example where MCPBA only reacts with one alkene, which is the more subalkene, right? Reacts with more subalkene, right? Since we make formaldehyde twice, do we erase one of them for our final product? Yeah, so you can erase one of them for your final product. And if you do that though, you would have to do 2 formaldehyde like that. You would have to draw a 2 right there. But if you draw it out like this, you're showing the 2 formaldehydes right here, one here and another one here, right? Because we form 2 formaldehydes, right? Okay. So the solvents that you can see with ozonolysis is either dimethyl sulfide or with zinc acetic acid, right? And then the first step can have an A product solvent like CH2Cl2 or THF, some A product solvent that would not do anything in the mechanism. The second step is some kind of reducing agent. Okay. I'm not putting stereochemistry here because this is not a chiral center, so I'm gonna put as flat bonds like that. So alkene stays like that. Okay. Okay. Next one, 9. Okay. So this one here, what's gonna happen in the first step of the mechanism? Let me draw out the CHCl3 out in Lewis structure, and that might give you guys a hint of what's gonna happen here. And let me draw that strong base out like this. Yes, a carbene intermediate is gonna get formed, right? This carbon here is attached to 3 electronegative chlorine atoms, which is going to withdraw electrons from that carbon, pull the carbon's electrons, making this carbon here partial positive and all these chlorines partial negatives. This partial positive carbon here is so unstable that it wants to become neutralized, and it's going to withdraw electrons from this hydrogen right here, making that hydrogen partial positive charge. And because of that partial positive charge hydrogen, that hydrogen is going to be very acidic. Another reason why this hydrogen is going to be acidic is because when we draw out the conjugate base, right? Like imagine that's no longer there, and we give this carbon a negative charge. This negative charge on the carbon is stabilized by the 3 electronegative atoms here, withdrawing on the electrons of that carbon. So this hydrogen here is going to be very acidic. So when you use any strong base like terbutoxide or even NaOH minus, the first step is an acid-base reaction. We're going to deprotonate that carbon by grabbing that hydrogen. The bond between that hydrogen and carbon is going to break and go to that carbon right there to give us this intermediate here, where the carbon has a pair of electrons and a negative charge now. Right? And you could draw terbutanol as a side product. This is unstable, right? Because carbon with a negative charge is unstable. But we have 3 good leaving groups here, 3 chlorines. One of them is just going to leave by itself to form this carbene intermediate here. Now, there's something special about this carbene intermediate. Do you guys know like what property makes this carbene intermediate special? Yes, there is an empty p orbital because it is electron deficient. It has 2, 4, 6 electrons, right? But this is weird because normally when we say an electron deficient carbon, like a carbocation, there is a positive charge there. But this carbon here is neutral. Because if we calculate the formal charge, carbon wants 4 electrons. It has 1, 2, 3, 4 electrons to itself. 4 minus 4, 0. So it's neutral. So because of the empty p orbital, this carbene is an electrophile. But because it has a pair of electrons right there, it is also going to be called a nucleophile. So it's a nucleophile and electrophile at the same time, right? So this carbene right here is an electrophile and nucleophile at the same time. Electrophile because it has an empty p orbital, missing electrons. Nucleophile because it has that pair of electrons that it could use to attack some electrophile. Right? Okay. Once we form that carbene, let's bring in our alkene. Because of the empty p orbital, this alkene is going to attack that carbon. And think of this as the bromonium ion mechanism we did earlier. As this carbon here is gaining electrons, this alkene is losing electrons. This carbon here is going to attack the other carbon of the alkene at the same time, using its pair of electrons that it has right there to form this dichloryl cyclopropane propane ring right here, right? Where that's the carbon attached to 2 chlorines like that. If I highlight this carbon in yellow, that's this carbon right there in yellow. Plus minus, because that could have been dashed as well. Okay. So there is another mechanism you need to know that is similar to this, which is the one with CH2N2. But it's going to be very similar. The first step is just going to be the one that's different, right? Because if you draw out the Lewis structure of that, we have this N2 right here, which is a very good leaving group. When we kick it out, we're going to form this carbene here, right? Which is going to do the same reaction with any alkene. But instead of having chlorines, we're going to have hydrogens on that cyclopropane. Okay. There's another reagent that you guys have to know, which is Simmons-Smith reagent, CH2I2, with zinc or copper, which will form a cyclopropane, but you don't need to know the mechanism for that, right? Don't worry about the mechanism for the Simmons-Smith reagent. Okay, let's move on to the next one. Number 10. Okay. What do you guys think is going to happen between this alkene and the first step? When you see multi-step reactions like this, first and second step, ignore the second step or any other step like 2, 3, 4, and just focus on the first step and what that would do to this reactant. What would this first reagent do to this alkene here? Alkene grabs Br, kick out the other Br. The Br being grabbed or attacks the other carbon at the same time, forming, what is the intermediate name of this reaction? This might show up as a multiple choice question or explanation question. But what intermediate gets formed here? What's the name of that special intermediate for this reaction? Bromonium ion. Yes. And in this case right here, water would want to do attack, right? But once we form this bromonium ring right here, notice how we have a bulky brittle group here on the wedge side. The bromonium ion ring is gonna be major on the dash side, like that, right? Oh wait, be right back. Be right back. I'll be right back. Okay, I'm back. So if this bromonium ion here is a dash, this methyl here is forced to become a wedge, right? And now we have a competition of nucleophiles. The Br minus that got kicked out earlier in this first step, and the excess amount of water product solvent we have. And water here would do an attack, right? It would attack the more subcarbon, and then do a backside attack. Invert the stoichiometry right there to give us this intermediate right here. This bromine stays as a dash. This is the new bond, the wedge bond, to this oxygen right there. The wedge methyl inverts to a dash. This oxygen right here that attacked that carbon is attached to 2 hydrogens. 1, 2. And because it has 3 bonds, it's going to have a positive charge. Where the last step is to deprotonate and neutralize that positive charge with HSO4 minus, reforming the acid catalyst H2SO4. You could use H2O as well to deprotonate it for the mechanism, giving us this major products here. And we cannot do plus minus because of that pre-existing chiral center at the terbital. So if I draw out the other product, we can only flip the 2 carbons, which were the alkene carbons right here. Like that. Okay. And then you could do plus minus like that for both. Okay. Oh, right. So this is the product for the first reaction. The NaH right here. Whenever you see Na, always associate that with a positive charge. So that means that whatever is attached to it is going to be negatively charged. So we have a hydride ion here, H minus, which is very unstable because we have a negative charge on a very small non-electronegative atom. Very unstable, which makes it very reactive. This is a very strong base and nucleophile. Base, nucleophile. right? So we have a hydride ion here, H minus. Think of it as a strong base. When we have a strong base right here, we're gonna look for the most acidic proton, most acidic hydrogen. Which hydrogen here would you guys say is the most acidic proton, most acidic hydrogen here? Right. OH, yeah. So this H minus here is going to deprotonate that alcohol. I'm gonna draw out the bond out between that O and H explicitly to show that those two electrons are gonna go onto that oxygen, giving that oxygen a negative charge, right? Okay, Br wedged O minus dash right there. Now we created a nucleophile here, the O minus, so that's our nucleophile. And we have an electrophile right here, that partial positive carbon with a good leaving group attached to it, bromine. We're gonna do an intramolecular Williamson ether synthesis reaction. This O minus here is going to attack that electrophile, kick out the leaving group, and form this epoxide right here. Right, and this is going to do a backside attack where we invert the dash bond into a wedge bond like that. This methyl stays as a dash. And the epoxide could have been a dash as well. So this is an intramolecular reaction because the nucleophile is on the same molecule as the electrophile. Right, this nucleophile oxygen minus here is on the same molecule as the carbon, partial positive carbon. And whenever they're on the same molecule, they're always going to form a ring, some sort of ring. And this ring here is the epoxide, right? All intramolecular reactions forms a ring. Like that. Yeah. So the first step was halohydrin formation, right? Where we formed this halohydrin. And then the second step was halohydrin to epoxide, Williamson ether synthesis. Does this happen every time? Thought that it was just Br and OH that forms. So it will be only Br and OH that forms if you did not have that second step of the NaH DMSO. Like if you just had Br2 and water as the reagent on this alkene, then you stop here at the Br and OH. But because we have a second step of NaH right there, that second step would do something to this OH, which would proceed with the Williamson ether synthesis. Yeah. So let me review Williamson ether synthesis. There's two reactions that go with this. The first reaction is an acid-base reaction. Second step is an SN2 reaction. Right, 2 steps for Williamson ether synthesis. It's gonna start with an alcohol, and we're gonna react that with some sort of base, right? And the second step is gonna be some sort of haloalkane to create an ether, right? It's in the name, Williamson ether synthesis. We're gonna synthesize an ether. There's 2 types. There's intermolecular Wes, and intramolecular Wes. So for the intermolecular Wes, let's say we have this alcohol right here, and we react it with these reagents. First step, NaH, DMSO. Second step, this haloalkane right there. The first step here, we have a negatively charged H- ion, which is going to deprotonate the alcohol, giving that oxygen a negative charge, O-. That's the end of the first step. Then we bring in the second step, where this O- attacks that partial positive carbon substrate to kick out that good leaving group and give us this ether here, like that, where this is the ether we formed from Wes. And this is intermolecular Wes because the nucleophile, this O- here, is a separate molecule than this electrophile. They are separate molecules. Intermolecular. Right. Intramolecular Wes is when we have the nucleophile and electrophile on the same molecule. So let's say we have OH right there, and we have Br right here. And in this case, we're just gonna have NaH DMSO, nothing else. Because our haloalkane here is part of the molecule as the alcohol, right? It's on the same molecule. So H- here deprotonates the alcohol, create the O minus, and then once we have that nucleophile, this O minus attacks that carbon, kicks out the leaving group, inverts stereochemistry, and forms that epoxide right there. Right. This is the new bond that gets formed, which is the inversion of that dash bond right there. Instead of that epoxide, we could have formed this bigger cyclic ether as well. Like we could have had this instead. Okay, NaH, DMSO, H minus, deprocyanate the alcohol, give this O minus right here, and then this O minus attacks that carbon, kick out the leaving group, and I'm gonna number this now. I'm gonna number my number 1 atom, that oxygen, number 2, 3, 4, 5, and stop at the electrophilic carbon. I know that I'm gonna make a 6-membered ring, so I'm going to draw that 6-membered ring out like this, where oxygen is the first atom. So that's gonna be 1, 2, 3, 4, 5, 6. Carbon 2 has a methyl group, and then carbon 6 also has a methyl group. This is when we fill in the decorations. Like if there's an isopropyl group here, isopropyl group there, then there would be an isopropyl group there. Right. Decorations. Right. But this is still a cyclic ether, right? A cyclic ether for intramolecular Wes. This is also a cyclic ether, but it's a special cyclic ether. It's the epoxide. Yeah, so the H minus here would attack this H because this H minus, the negative charge on this H right here is unstable. And the reason why it's unstable because hydrogen here does not want this negative charge at all. This hydrogen is so unelectronegative, right? It's the least electronegative atom, and it's so small. It cannot handle this negative charge. So this hydrogen here is very angry right now. And because this is a very angry hydrogen, it's very reactive, very unstable, very reactive, making it a very strong base. It's a very strong base. It wants to become neutral again, you could say, like that. It wants to get rid of that negative charge as soon as possible. And because this is a very strong base, it's gonna look for the most acidic hydrogen, which is this alcohol hydrogen right here. This hydrogen is acidic because it has a partial positive charge since it's attached to this electronegative oxygen atom right there, right? And this partial positive charge of the hydrogen here attracts this negative charge. Opposite charges attract. So this is our acid, right? The OH, this is our base. We're gonna do an acid-base reaction here. This base is going to attack that hydrogen, grab that hydrogen, and at the same time, the bond between the hydrogen being grabbed and oxygen right there breaks and goes onto the oxygen right there, giving us this O minus right there. And we're gonna form H2 gas as a side product, right? Which is now happy and stable. Right, we get rid of that negative charge, that unstable negative charge on a very small non-electronegative hydrogen atom. Instead of NaH, you could use a strong base like LDA, right? Like this. Diisopropyl. Yeah, like that. Or any strong base, like any strong base that can deprocyanate or rip off that hydrogen from this alcohol. Right. But usually I see NaH as a common reagent for this Wes reaction. Okay. So that right here, this one here specifically, is the halohydrin to epoxide reaction from Helix's study guide. Halohydrin to epoxide, aka intramolecular Wes, intramolecular Williamson ether synthesis. Right. A halohydrin is this, where we have a halogen next to a hydroxyl group. Halohydrin, halogen next to hydroxyl, going into epoxide. That's intramolecular Wes. Okay. Any questions on this reaction? Okay, let's move on. And 11 right here. Okay, so this reaction here, hydrogenation, would this be a syn addition or anti-addition reaction? Syn addition reaction, yes. So there is gonna be a major and minor product here. Do you guys want the hydrogen to be on a wedge or a dash here in the product? A wedge, yes, because of these bulky turp butyl groups on the dash already. It doesn't want to go on the backside because it's too crowded. It's too crowded there, right? It wants to go to the side that has more space, which is the top side, the wedge side. So these turp butyls stay as turp butyls, as dashes, and then the major product will have hydrogens on the wedge side, forcing the other R groups to be a dash, right? So that's the major product. If you draw out the minor product, this is what it would look like, where the hydrogens would be dashes instead. And these R groups would be wedges, like that. And it's kind of counterintuitive because if you look at the R groups, right, the R groups here are all on the same side, like they're all dashes. And it looks very crowded like that. But this is still major because of the way the hydrogen approaches this alkene. The hydrogen has to approach the alkene on the less sterically hindered side, less crowded side, right? Which leads to like a more crowded molecule, you could say, right? This minor product here looks more stable because the R groups here are like having less steric hindrance, but it's minor because of the way the hydrogen approached this alkene, right? The hydrogens here are going on the backside, which is very crowded to go in the first place, right? Okay. What reaction name do you guys think this is gonna happen when we have this alkene reacting with H2SO4 and heat? What is that reaction name? Isomerization, yes, because we just have acid and heat, where if we just have acid, let's say we protonate this alkene right here to form this carbocation. Right. This carbocation here now has a single bond, which can do free rotation. And if I rotate that like that, I can either grab this hydrogen, making that alkene right there, which gives me this product, or I could grab this hydrogen, making this alkene right here, giving me this product right here. So we get two different products here, this E alkene or this E alkene. Right, so those are our two major products. So normally in isomerization reactions, you guys are used to seeing like converting a less substituted alkene to a more substituted alkene like that, right? So that is the regular isomerization reaction, where we form the more stable alkene. But it could be tricky because we are still making the more stable alkene, right? This is a Z alkene, whereas these alkenes that we just formed here are E alkenes. That's still the more stable alkene, even though they're both di-substituted. Right? The Z alkene and the E alkenes here are di-substituted, but the E alkene is more stable. Is 11 racemic? These two here are not racemic because of these butyl groups here, but once you draw out the two diastereomers, like this diastereomer and this other diastereomer, you can do plus minus for both. But make sure to draw out both diastereomers first, and then you could draw the enantiomers of both diastereomers. Right, because the carbon center here with the butyl groups stays untouched. Nothing touches those carbons, so they stay as dashes. Whereas the alkene carbons here are the ones that are changing. Right. Okay. Okay, so any questions on predicted product here that we went over? Once we have the two products, do we need the plus minus? So Helix does the plus minus when he does the diastereomers. So I would for his class. Just in case. Just to be safe. Just to be safe. Okay. Right. Yeah. Right. Okay. This is not meso because there is no plane asymmetry, right? Like this one here is not planar symmetry because of this ethyl group and that methyl group right there. They're different. If they were the same molecules, however, like let's say this was a dash methyl, then that would be meso, right? Mm-hmm. Yeah. If it was meso, it would still be racemic. So, if it was meso, we cannot say racemic because racemic is a 1-to-1 ratio of enantiomers, and enantiomers are chiral, right? Enantiomer molecules are chiral. Meso molecules are not chiral; they are achiral. Even though they have chiral centers, right? The overall molecule of a meso molecule is achiral because of this planar symmetry. And because of that achirality, we cannot say enantiomers or anything anymore. Right. Mm-hmm. Yeah. So that's all 118A. I like how you guys are still thinking about 118A. He won't ask a question about like meso or anything like that here. But stereochemistry is still tested on the product, like syn addition, anti-addition, and like whether or not you could do plus minus or not. That part of the stereochemistry is tested, right? But I don't think meso will show up for the exam. But that's good that you guys are thinking about that. Uh-huh. Who did you guys have for 118A? Levens or who was the other teacher that taught 118? Wei. Wait, was it Levens and Wei last quarter? I think, yeah. Wei, yeah, I see. Hey. Okay. Let's move on to. So I kind of like went over explanation a lot already, so let's skip that and go over synthesis because when I was doing all the mechanisms for these predicted product problems, I was explaining like in detail why it's in addition, why it's anti-addition, the intermediates, the base, the acid, and everything. So like the explanation question is testing your conceptual understanding of all those mechanisms, right? Like why it's anti-Mark versus why it's Markovnikov, why it's in addition, why it's anti-Mark. So let's skip that. We can go back to it if you guys have questions, but I want to go over synthesis here. Farhat. Oh my god. Oh yeah, Farhat was the one that's at 118A. Oh my god. He was like his tests were so similar to his practice exams. Yes. And he would say what was that? Like easy? Second one? Okay. Okay. Have you guys had the chance to try these out? Do you guys have any questions in particular you guys wanted to try out? I know Mazna said she wanted to try out 4 to 7, so we could go over that first. So let's start with 4. For synthesis problems, here's my thought process. I look at what's similar and what's different. I'm gonna highlight the part that is similar, which is this ring right here, right? And then I'm gonna circle the one that is different. See, yeah, it's a lot of reactions. Like think of the reactions that you learned as the tools in your toolbox for these synthesis problems, right? And then for synthesis, you're gonna like try to remember all the reactions that can do like different transformations to convert a reactant molecule to a product molecule. The more reactions you know, the more ways you could solve like synthesis problems. And there's multiple correct routes for synthesis sometimes, right? Some routes would have more high yield, some routes would have lower yield, but some routes would be equally the same, right? So what I recommend to study is that first, understand the mechanism for all reactions conceptually, detail, step by step, arrow by arrow, charge by charge, electron by electron, and talk yourself through it as you go through the mechanism. Explain yourself why it's syn addition, why it's anti-addition, why it's Markov-Nikov addition, why it's anti-Markov-Nikov addition. And when you know, like, understand each reaction in detail like that, I know it's hard because there's a lot of reactions and you guys have a note card, so you guys are planning to just like, write the mechanism in your note card. But try to understand it because that would like really help you with these reactions. And then also the chart I gave you guys here, associate these reagents with the reaction right here, right? Like whenever you see these reagents, always think about what reaction it does based on the functional group. In this case, it's alkene. And then for synthesis, it's bringing it all together. It's like a puzzle. It's like a you bring all those reactions together like that. What is the best way to approach synthesis problems? So the best way, well, are different approaches for synthesis problems, right? The way that I approach synthesis problems is that I find what is my similarity between the reactant molecule and the product molecule, which I highlighted here. Like this cyclopentane with the methyl group right there is the same, right? And I circled here the differences. Like the differences could be a new functional group, a new carbon-carbon bond, which is a sign of what? Like if you see a new, let's say this is OH and you have like a new carbon-carbon bond. What reaction do you guys think happened there? Somewhere in the synthesis route. If you see a new carbon-carbon bond. Like, this is a 1:A reaction. 1:A. Starts with G, Grig. Grignard, yes, Grignard reagent. When you see new carbon-carbon bonds, that's the sign of Grignard reagent. Correct. Another thing that you guys can look out for is the regioselectivity of these things, right? Because we see that this bromine here was on a more subcarbon, but we saw that in the product, it's now on the less subcarbon, the anti-mark carbon, right? So now, once we do that, we can start like thinking about what reactions add bromine to the less subcarbon. What reactions do you guys know that we just learned about and we just went over today adds bromine to the anti-mark carbon, to the less subcarbon? Roar. Yes. What sound does a lion make? Roar. So when you see a less subcarbon like that, think of a lion. And think of roar, right? Which is going to do anti-mark reaction, right? Okay. So we could go backwards here. This is retrosynthesis. Retrosynthesis is a strategy for synthesis where you go backwards and say that came from HBr, roar, and heat, which means that the alkene must have been from here, going backwards. Retrosynthesis. Right. Okay. So now we see that we have this alkene right here, and we're going to try to convert this molecule into this alkene right here. You guys notice how this is like a less stable alkene? What reaction do you guys know that forms a less stable alkene? 1:A reaction. E2 Hoffman, yes. Bulky, strong base for E2 Hoffman. So we could go backwards even further and say that there was a leaving group right here, and we could use a bulky base. You could either use tert-butoxide or LDA to do E2 Hoffman, yes. Okay. Now we see the bromine is now here, right? What do you guys think it was in between these two carbons here? Like what functional group do you guys think was right there? Somewhere in the intermediate. A bromonium ion ring. So if this was a bromonium ion ring, like let's say that was a bromonium ion ring with a positive charge, there's 3 scenarios that you could react this bromonium ion ring. One with an A product solvent CCl4, one with water, and another one with ROH. If you had CCl4 as a reagent, you're gonna have bromine on both carbons as a product, right? Like bromine here and another bromine there, and tied to each other. Like let's say dash wedge like that, and that's still the ring like that, right? So that's the CCl4. If you use water, then you're gonna have OH. If you have alcohol, then you can have OR. Right, but in this intermediate here, we have bromine and hydrogen on the other side, right? So if you have bromine on the Markovnikov side, the more sub side, and hydrogen on this side, there was an alkene right there. Yeah, not oxymercuration demercuration, because oxymercuration demercuration adds alcohol on the more sub side, right? Or if oxymercuration demercuration reacts with water, you would have OR on the more subside. We don't have OH or OR on the more subside. We have a bromine on the more subside. So going backwards, HBr with that alkene right there. Yes. Nice. Yep. Alkene right here. And when we react this alkene with HBr, we're adding bromine to the more subside right there. Nice. The mercury one adds alcohol or ether on the more subside. Now, what reaction converts this haloalkane to this alkene right here. E2 itself, yes. And that can be a small base. Helix loves these ethoxides, so let's use what Helix loves right there. It could also be NaOH or water as well, or any small base. It could be even NaH that we talked about, NaH, DMSL. But Helix loves these ethoxides here for E2 itself. Okay, so summarize everything. The first step, E2 itself. Second step, hydro halogenation or hydrobromination to be specific, or addition of HX. Third step, A2 Hoffman. And then last step, radical addition of HBr, ROR. Right, so what I did was found the similarity between the reactant molecule, product molecule, find the differences between them, and then look at the properties, like, and start thinking about reactions to go backwards, retrosynthesis. And when you get stuck, try going forwards, and then try to meet in the middle, at the end, right? And then once you get more like intermediates and get closer, it starts to get easier to think about what reactions can do that. Okay. Any questions on this synthesis problem? Okay. Let's move on to number 5. So let's do the same thing. Here is the similarity between this reactant molecule and that product molecule there. This cyclohexane with that methyl group right there. Cyclohexane with that methyl group right there. Here are the differences. Alcohol, and bromine. So we do still have an alcohol here, but it's in a different position now. So you guys notice how the bromine here and alcohol are adjacent to each other, vicinal to each other, where alcohol is on the more subside. What reaction comes to mind when you see an alcohol on the more subside and bromine on the less subside that are adjacent to each other? What reaction comes to mind for you guys? Let's go backwards. Retrosynthesis. All right. When you see two functional groups like next to each other, you could assume that this was an alkene. This came from an alkene. Yes. Right? So there was an alkene right there, which reacted with Br2 and water to form this halohydrogen right here. Yes. And we went over the mechanism of this earlier, and we said why like water attacks the more subside already. So that's all the conceptual part of that and explanation of that done. And then once you know that, you bring it together in this synthesis type problem. Okay. Now, this is like the less stable alkene, which we can form from E2 Hoffman, like we said, using LDA, let's say. Sure, this is a 6-membered ring. Let's say bromine was right here. Okay. And we see that bromine is at the more sub position. And let's say there was an invisible hydrogen there, right? Because of this hydrogen and bromine, HBr is the reagent that comes from this alkene right there. Okay. Now, what reaction do you guys know that can create an alkene, a more stable alkene from alcohol? Right. Yeah, H2SO4 and heat to favor the elimination reaction, which is going to form the more stable alkene. Yes, alcohol dehydration. Right, if this was a halogen, like a Br or chlorine, to form this alkene, that would be something else, right? That would be like a small, strong base for E2. But because this is not a Br or chlorine or a good leaving group, we're going to have to do alcohol dehydration to form the alkene, right? Because there's two ways to form alkenes that you guys learned about. Elimination reaction like E2 or E1 with a good leaving group like bromine, or alcohol dehydration, which is what we did here. Alcohol dehydration. And then we did hydrobromination. And then we did E2 Hoffman. Right? We could do E2 here because we have a good leaving group present now, that bromine. And then we did X2 with water. Halohydrogen formation. halo hydrogen formation. Okay, next one. So let's do the same approach. Find out the similarities between the reactant and molecule. Here is what is similar, the yellow highlighted part of the molecule, and I'm going to circle the differences. This bromine and these two alcohols here. And do you guys notice how these two alcohols are anti to each other? Like one is wedge, one is dash. They're also vicinal, right? What route comes to mind? Right. MCPBA. So there was an alkene here, right? So when we go backwards, that could have came from an epoxide like this, right? And the way that I'm drawing it here is gonna be like this, right? Where you notice how this wedge OH here is that wedge oxygen right there. If I want to maintain this stereochemistry right here, then I have to attack the wait, actually here it doesn't matter here because they're both equally substituted. So you could use NaOH and water or H2SO4 and water. If these were like asymmetrical and you drew this as wedges, it would matter what you use because basic conditions attack the less subside, inverting the stereochemistry at the less subside, whereas the acidic conditions would attack the more subside, inverting the stereochemistry at the more subside. But in this case, it doesn't matter because they're both equally substituted, right? So this is opening up epoxides in acidic or basic conditions, which creates two vicinal diols, which this epoxide could have came from this alkene right here using MCPBA. Like that, right? Okay. Now, what do you guys think happened to convert this haloalkane to this alkene right here? I'll give you guys some time to think about those reactions that will convert this haloalkane to this alkene right here. H2SO4 and heat, that would react with alcohols. Hydration, that would be alcohol. Right, we don't have an alcohol here present, so we can't do H2SO4. H2SO4 would not do anything with this halogen right here. If this was an alcohol, right, then we could go directly to there with H2SO4 and heat, but that's not an alcohol. So we won't do alcohol dehydration here. We're gonna do E2 by itself with, let's say, ethoxide to form this more stable alkene. No, not there. Right here. And then from this tri-substituted alkene to that tetra-substituted alkene, there's two ways that we could actually do that. What is one way that you guys can think about to convert this less stable alkene to the more stable alkene? Isomerization, yes. We cannot do E2 again because we don't have a good leaving group here present, right? We can only do E2 when there's a good leaving group present. So if you want to do it again, that's the other route, but the faster route would be isomerization, where to go directly to the more stable alkene, you use H2SO4 and heat. The longer route would be if you wanted to do E2 again, you could do HBr, creating a good leaving group on the more sub position. And then for that more sub position, you could create that more stable alkene using a small strong base like that. Right. So you could go this route as well, and Helix accepts both routes. Right. If this Br here at the very beginning was an alcohol, you could go directly straight to this alkene by using H2SO4 and heat for alcohol dehydration. But we can't do that because this was not a BOH. This was a Br leaving group. So we had to do E2 first, and then isomerize that to the more stable alkene. Or if you want to do it again, create another good leaving group at the more sub position, and then do another E2 by itself. Okay. Would we have been able to use dihydroxylation in the last step? So dihydroxylation would not do anything with this epoxide in the last step, but if we did dihydroxylation from this alkene right here using osmonium tetroxide and H2S, that would form the two alcohols vicinal to each other, right, on the same side, but syn addition. So both alcohols will be on the same side. If one is wedge, the other one would have to be wedge as well. If it is dash, then the other one would have to be dash as well. But we don't have syn alcohols, we have anti-alcohols. So we have to go through this epoxide and then open it up with acidic or basic conditions. Doesn't matter here. Right, so osmotic hydroxide is the other route, which makes the two alcohols syn to each other. Yeah. Yeah. So if this was your product in synthesis instead, right, then you would do this route here. Right, so, but we didn't have that, so we wanted to go through this route here. Okay. What's the difference between Zaitsev and Markovnikov? So that's going to talk about, let's say, Zaitsev is used to compare with Hoffman, right? If you have this haloalkane right here, and you react it with two strong bases, like one small strong base, and then the other one is a bulky base. The small strong base is going to create the more stable alkene, Zaitsev, whereas the bulky base is going to create the less stable alkene, Hoffman, less substituted alkene. For Markovnikov versus anti-Markovnikov, there's a lot of reactions that goes with this, right? So an example would be like, let's say we have this alkene reacting with HBr. Right, let me separate it like this. HBr versus HBr with ROR and heat. The HBr one would go through the Markovnikov, which adds bromine to the more subcarbon. Whereas the HBr with ROR adds bromine to the less subcarbon. Another one that you could see is oxymercuration demercuration, right, with either H2O or ROH as the nucleophile in a product solvent. Second step, NaBH4, NaOH water. Or the second way you could do is hydroburst oxidation with BH3, THF. Second step, H2O2. NaOH water. The first one is oxymercuration demercuration, where you're gonna add either OH if you use water or OR if you use alcohol on the Markovnikov position. Right, but if you use hydroburst oxidation, you're gonna add alcohol to the less subcarbon anti-Mark position. So for Zaitsev Hoffman, it's talking about alkenes. For Markovnikov versus anti-Markovnikov, it's talking about electrophilic addition reactions. Do with alkene placement, while Markovnikov is about substituent replacement. Yes. Right. So this is talking about alkenes, and this is talking about substituent, aka electrophilic addition reactions. Electrophilic addition reactions. Yes. Yeah. Okay. So both would be regioselectivity though, because it's talking about the region where the alkene is or the substituent is. Stereoselectivity is like where they are in space, like syn addition, both on the same side, or anti-addition, one they're on the opposite side, right? Okay. Number 7. Okay, so this one here, the reactant molecule and product looks totally different, right? But what reaction is calling out for you guys right now? What reaction is screaming at you guys right now when you guys see this? We want to break a bond to break open the ring. And the reaction that breaks open the ring or breaks a bond is ozonolysis. Right? So if we do ozonolysis, what functional group gets formed? Like what functional group is always there whenever we do ozonolysis and we break open an alkene? It won't be always an aldehyde or ketone, right? It could be both, like aldehyde or ketone. more specifically a carbonyl, carbon double bond oxygen, right? Which could be an aldehyde or ketone. So let's go backwards here and say that those alcohols came from a carbonyl. In this case, the carbonyl is a ketone, but we can't always say that for all cases because some aldehydes like are gonna, I mean, some carbonyls are gonna be aldehydes like that or this, right? But it will be a carbonyl, a carbon double bond oxygen like that. What reaction from 118A converts a carbonyl to an alcohol? Jones is an oxidizing agent, right? So that's oxidation. But here we're doing reduction, right? We're gonna reduce a carbonyl to an alcohol. So we gotta use a reducing agent, either NaBH4 or LiAlH4, that reducing agent, which is gonna reduce the carbonyl to the alcohol. And this is like on his study list, like one of the 118A reactions that you guys have to know, right? Okay, now let's number the distance between the carbonyls. 1, 2, 3, 4, 5, 6. Right. And you guys notice how there is a methyl group here and an ethyl group here at the end? We can say that that's this methyl group there and ethyl group there at the end, which means that there was an alkene right here. So if we go backwards here and say that there was an alkene right there, and we cut it open with ozonolysis, right? First step, O3, second step, H2S or dimethyl sulfide. That would cut this double bond in half, put two oxygens in the middle to get that right there. Do you need both? Oh, you only need one. You only need one. You don't need both, right? This is NaBH4 or LiAlH4. Yeah, only put one. NaBH4 or LiAlH4. Yeah. Now, what reaction can form this alkene from that alcohol? Right. Think about the ways we could form alkenes and think about the starting material. Do we have a good leaving group or do we have alcohol? And based on that, what reaction do we have to do to make the alkene? Right. H2SO4 and heat. Yes. Alcohol dehydration. When you have an alcohol and you want to make the more stable alkene like this, we do alcohol dehydration with H2SO4 and heat. If this was a bromine, we don't do that. We do E2 itself with a small base. Right, if that was a bromine. Okay. Okay. Let's do these ones here. For 8, let's highlight the similarities, which is going to be this part of the molecule right here. And the differences are going to be those functional groups right here. Okay. What reaction? Yeah, going backwards with the carbene CH-Cl3, strong base, like turbotoxide, coming from this alkene right here, right? So going backwards, the alkene was right there to form this dichlorocyclopropane with CHCl3 and turbotoxide. Okay. Going backwards, what reaction would you guys say if we go backwards more? E2 Hoffman. Yes. E2 Hoffman. Oh my gosh, you said that so quick. You were ready with that question. Oh my gosh. Okay, so let's say there was a bromine right here. So if we have E2 Hoffman, we could use LDA or turbotoxide. Let's use LDA right here. Notice how bromine is at the left subcarbon. What reaction, if you go backwards even more, creates this bromine at the left subcarbon, anti-marker position? Roar. Yeah. What sound does the line make? Roar. Say alkenos right there. HBr. Roar. Heat. Okay. Now we have this alkene right here on the moist subposition, and we have this aldehyde right here. What are the two ways that I said earlier that we can form alkenes? Like, what are the starting, what are the two reactions that you guys learned that can make alkenes? There's two. Right. Depending on what reactant you start off with. One was Dehydration with alcohol. Yes, that's one way to make alkane, alcohol dehydration. And the other way is E2 reaction with a good leaving group. What's more likely to come from this alkene? An alcohol or a leaving group? Like bromine, if we have this aldehyde right here. Like what's easier to make from this aldehyde? An alcohol or a good leaving group? An alcohol. Yes. What reaction can we do to convert that aldehyde into an alcohol? So this alcohol right there. Yep, NaBH4, reducing agent. Where this carbonyl carbon right there is that carbon of the alcohol right there. We want to reduce that aldehyde into this primary alcohol using first step, NaBH4. Second step, acid workup. Okay, and then like Sharon said, we can convert this primary alcohol to that alkene using alcohol dehydration, H2SO4 and heat. Right, we don't do E2 that stuff. Right, we don't do strong base because this is not a good leaving group, alcohol. We do alcohol dehydration to get to this alkene right there. Okay. So first step, reduction. Second step, alcohol dehydration. Third step, radical addition of HBr. Fourth step, E2 Hoffman. Fifth step, dichlorocyclopropionation. Do you think his questions will have... No. His questions will most likely have 3 to 4 steps, right? Because if you guys look at the previous examples that he went over, the key will have like 3 to 4 steps, right? But it's still good to, you know, understand these more tough synthesis problems so then you guys have an idea of how to approach them and it will be more clear, right? Because let's actually try his synthesis problems here from the previous exam. Let's look at question number 9. This one here was actually pretty tough for this quarter. I remember this one was pretty tough. I'm gonna have you guys try it actually first before we check the key. Practice problems of 118A reactions. I can send you my folder of my 118A content review, which has practice problems over there for you guys to check out. So let me actually do that now so you guys can review. Let's see, 118A. This was when I was back at Davis doing the 118A content review session. Let me share this with you guys. Anyone with the link, copy link, Zoom. Everyone in meeting. Here we go. Yeah. Okay. How many carbons do we have in the product molecule? 6? What about the reactant molecule? How many carbons do we have in the reactant molecule? 7? Yes. We see that we got rid of 1 carbon and we have a carbonyl here. What reaction comes to mind when you like cut a bond in half to get rid of a carbon, eliminate a carbon, and have this carbonyl here? Ozonolysis, yes. Where this ozonolysis reaction here, that carbonyl, came from this alkene where the methyl group is right there, right? So if we go backwards here, ozonolysis, O3, second step, dimethyl sulfide. You could draw it like this if you want. Came from this alkene right here. Right. Okay. Now, if we go backwards even more, we see that this is less substituted. So what reaction could have made that less substituted alkene right there? That was a good leaving group right here. LDA or turbotoxide. Yes, E2 Hoffman. Okay. Now, I'm gonna have you guys finish this off. What sequence of reactions would convert that into this right here? Going backwards, HBr, where the alkene was right here. Okay, now how can we create that alkene from this reactant here? E2Z yes. Let's use Helix's favorite small base, ethoxide. Right. This was tricky because he should have put this as the other product as well for the synthesis, because that does get formed from this last step here, right? Where the first step here, yeah, right. This one here like threw a lot of people off. I remember this quarter. It was weird. It was a weird question. But if he put this as the other product, it would start to make more sense, right? Because it does get formed. So he should have put that other product as well. Because like that does not disappear into the void. Like it's still there. Okay, so that was section A with the 2023. I don't have the blank copy for 2023 section B, so we're gonna block it off. Don't look at the key, right? No spoilers. So let's go to B and let me block it off. Let's see here. That's mechanism. Okay, let's do this. Oh wait, no, that's the key for A. Okay, let's go to B. Yeah, I don't have the blank copy for this one. Okay. Okay. Ooh. Does someone want to walk me through this synthesis problem and what the thought process is for this one? Yes, we add OCH3, which is this OCH3 right here, and we have an alcohol right here. And where do you notice the OCH3 is at? Is that the more subside or less subside? Like if you compare these two carbons right here, more subside or less subside? More subside, right? So if we go backwards here, and let's say that came from an epoxide, where this alcohol is the epoxide oxygen, right? That would have to be a wedge oxygen, and this would have been a dash methyl. If I want to add the OCH3 to the more subside, are we going to open the epoxide up in acidic conditions or basic conditions? So this is a 118A reaction here. Opening up epoxides, acidic conditions, right? So it would be CH3OH H2SO4, which is going to add this OCH3 to the more subside, inverting the stereochemistry, right? We're going to invert that wedge to a dash, inverting this dash methyl to a wedge methyl like that. Okay. Now what reagent creates an epoxide that you guys know? What 5-letter reagent? MCPBA. Yes. So let's go backwards a bit more. MCPBA, creating this alkene right there, like that. Okay. Now, what reaction can make that alkene from this alcohol? Alcohol dehydration with H2SO4 and heat. Why can't we use E2 that's a small base like ethoxide? Why can't we do that to make that alkene? Yeah, it's an alcohol. It's not a good leaving group. It's not a haloalkane. Yes. If this was a haloalkane, then you would go do the E2 side stuff. You do not do E2 sides, the alcohol dehydration. So keep those two different ways to form alkenes in mind. If you have an alcohol, you do alcohol dehydration. If you have a haloalkane with a good leaving group, you do E2. Either Zaitsev or Hoffman, depending on what alkene you want. Okay. So first step, alcohol dehydration. Second step, epoxidation. Third step, opening up epoxide in acidic conditions. Oh yeah, this OH is deceptive here because this OH here is not the same OH as that OH right there, right? Because if I highlight this OH right here in red, right, that OH is going to be here as a side product. When you draw out the whole mechanism with H2SO4 and heat, this OH will leave as a water leaving group. But if I highlight the OH in the product in yellow, that's somewhere in the MCPBA here. Right. So that's deceptive right there. Right. That's this epoxide oxygen right there, which is not the OH originally. Okay. And this OR here, OCH3, is coming from this OR right there. Okay. So helixes synthesis problem are like 3 steps, 3 to 4 steps. 1, 2, 3, 1, 2, 3, like that. It could be a little bit tricky though, because it could be deceptive, like this OH and the ozonolysis one, which is a tricky one. Okay. Are there anything you guys want to go over for the last 5 minutes of this review session? Any specific thing you guys want to go over? Number 9, synthesis. Let's do that. Have you guys finished your note card yet? When do you guys have your midterm? I know some people have tomorrow, some people have it on Tuesday. Oh, I've been doing it right now. Tomorrow. It's a work of art. I see. Tomorrow. Okay. 1 p.m., right? I haven't started. Wait, Vladimir, you have yours on Wednesday if you haven't started yet, or is it tomorrow still for you? Where can we access winter quarter 2023 midterms? You could access it here, but try not to. Well, I don't know. I guess it's okay because Helix didn't release this one, so I don't know if like he allows. Well, it's okay. Okay, here you go. Yeah. So number 9 and number 10 synthesis. Yeah. Let's look at the similarities, which is this yellow highlighted portion right here, which is this yellow highlighted portion right there. Okay. And now let's look at the differences. The alkene and this SR here. Now, we look at the SR and we see that if there was an alkene right here, it's at the less subcarbon. What reaction do you guys know that puts SR at the less subcarbon if that came from an alkene like that? Roar, yes. Where we can't do HBr roar, we do RSH and roar because we're not putting bromine at the less subside, we're putting RS in the less subside. So RSH with roar. Right. Now, that's as far as you got. Okay. So let me ask you this. What alkene does this look like? Does it look like the less stable alkene or the more stable alkene in its position right now? Less, right? What reaction comes to mind when you want to make the less stable alkene? E2 Hoffman. So let's go backwards further and do LDA and put a bromine right there. Okay. Now, where could this bromine could have come from? Like what reagent? If there was a hydrogen right here, invisible hydrogen right there. HBr, yes. And let's say that came from this alkene right here. Okay. There's 2 ways to go from here to here. There's a fast way, 1 step, and there's a slower way, 2 steps. What way can you guys think of that would convert this alkene to this alkene? Isomerization with H2SO4 and heat. Yes. That's the fast way. The slow way would be HBr to form. If we do HBr, would the bromine form at this carbon or somewhere else? If we do HBr or this carbon, either. So when we form HBr, think about the mechanism here. What gets formed as the intermediate? Right, when we protonate this alkene, what gets formed? What's the special name of that intermediate with HBr? Carbocation intermediate, right? The bromonium intermediate comes from Br2 and either CCl4, water, or alcohol. That's when you make the bromonium ion ring, Br+. For epoxide, that can come from like 2 ways. That could come from MCPBA, or that could come from opening up that could come from a halohydrin, right? BrOH from intramolecular West, Williamson ether synthesis. But if we have an alkene with HBr, we're gonna form a carbocation intermediate. And whenever we have a carbocation intermediate, what step do we always have to look out for, right? Like let's say we have a carbocation right here, a shift, a hydride shift or methyl shift. So we're gonna do a hydride shift over there, which is why bromine is going to be on that side if you do HBr, not on either side here. Even though they're equally substituted, we prefer the carbocation to be here first in order for us to do a hydrate shift to form a carbocation there, right? So when you see a strong acid like HBr or H2SO4 with an alkene, always think of a carbocation intermediate, which can possibly do a shift, right? And then from here, we could create this alkene using a small base ethoxide like that. Okay. Number 10, right here. Yeah, you didn't have to do this route here. The blue route was like optional. You could have just went straight to the more stable alkene using isomerization, H2SO4 and heat. But if you go through this route here, you cannot skip this step, right? Because actually, hold on. Wait, this thing is this thing right here. So, oh whoa. So you could go from this alkene straight to this halocane that we want eventually with HBr. So this right here would actually be the faster route. Oh, that's interesting. Okay, yeah. So if you did isomerization, that would be the slower route in this case, right? Because you would have to go through HBr to get this. But if you just go directly with HBr with the hydrate shift, you could just go straight to here where we want anyway. Yeah. So this right here would be the faster route. HSR and HBr in the same synthesis is funny. Yeah. HBr, HSR. Yeah. Skip. But both routes would work. Yeah, I made up these synthesis problems myself, and the way that I made it was like I looked through his study list, what reactions are tested, and then I tried making synthesis problems randomly that has a random choice of different reactions. Right, but I didn't go over the key myself before sending this out. So I didn't know what the key was, right? I didn't know if there was gonna be a typo or if there's gonna be multiple routes, just like this one. Like I didn't realize that this was the other route that could work. But Vladimir, you got it. Like we could skip that step as well. But I didn't like have that planned when I first made this. Like the original intended route that I wanted you guys to do was this route right here, which was my thought process when I made this synthesis problem. I didn't think of this one here. But working through it, like I now know that this is the faster route. What's the name of the last step? This one here is gonna be radical addition. On the study list, Helix calls it, there's different names, but Helix calls it, what does Helix call it? HBr or HSR plus ROR. HBr on the study list. It's at the end of the reaction list. HSR plus ROR. Radical addition of HBr or radical addition of HSR. You could also call it like that. Right. Okay. Now for number 10, let's highlight that and highlight this. And look at the differences. Bromine, alcohol, and ethyl. We have a new carbon-carbon bond here. What reaction does that tell you that we have in the synthesis? If we have a new carbon-carbon bond. Grignard, yes. MGBr. And this alcohol here came from the carbonyl, right? So let's say that this pink carbon I'm dotting right there is the carbonyl carbon, and this starred carbon here was the MGBr carbon, the nucleophile. If I go backwards here, right, that pink carbonyl carbon is that pink carbon right there, right? Because this carbonyl oxygen here is gonna eventually become that OH. But when we do the Grignard reagent, I know that this starred carbon is our nucleophile, which is directly attached to the MGBr. And then the second step is acid workup, H3O+. Because this negatively charged carbon here, when it attacks that carbon and pop this double bond onto the oxygen, that oxygen will have a negative charge, O-, single bond O-. But to protonate it to have OH and neutral, we bring in the second step, H3O+. So that's the Grignard reagent, right? What reaction? Like where do you guys think this carbonyl came from? What functional group do you guys think this came from? this carbon neo here, carbon double bond oxygen. An alkene. Oh, you can say an alkene, right? Or an alcohol. But the way that I wanted you guys to do was an alcohol, right? Which is OH right here. Because what are we doing here with this alcohol? When we convert that alcohol to this carbonyl, are we oxidizing or are we reducing? Oxidizing, right? And there's two reagents you can use here. You can use Jones or PCC, it doesn't matter, right? Because this is a secondary alcohol. It would matter if you have a primary alcohol, but because this is a secondary alcohol, it doesn't matter what oxidizing agent you use, PCC or Jones. But what Katya said, if you try to make an alkene, like coming from that, like this alkene right here, you would have to do ozonolysis, second step, dimethyl sulfide, which we can try to get this intermediate, but I did not think about that when I created this problem. I thought about this route. So let's do this route first, and then let's try to go through this route here later. Now, what sequence of steps do you guys can think of that we could convert this into this right here? Right. You could think about it going backwards or forwards, either way. Whichever way is easier, looks easier for you guys. So halohydrin is when we have Br and OH adjacent to each other like that. Right. If you see OH here, right next to this tertiary position, think of this as a less subcarbon. What reaction adds alcohol to the less subcarbon, antimark carbon? Right. Let's say there was an alcohol, alkene right here. What reaction adds an alcohol? Oh wait, hold on. I just realized something. We can't go directly from this alkene because they're equally substituted, right? So we have to actually go from this alkene right here. Oh, Peyton, I like what you talked about. That first step right here, the CH3 COONA, that would convert this into an ester, and then the second step would convert that ester to an alcohol, right? But the alcohol is gonna be on this carbon here if you did that, right? Yeah, so it's not gonna be on the right carbon. If we have this alkene right here and we want to add an alcohol on the less sub position, that's gonna be hydroboration oxidation. First step, BH3, THF. Second step, H2O2, NaOH, water, right? If this was our alkene right here, and we did hydroboration oxidation, we add alcohol on the less sub position, antimark position, right? Now, how can we make an alkene from this haloalkane right here? If we have a haloalkane, what reagent do we have to use to make an alkene there? Right. Roar. The roar would add bromine or SR to the less subside from an alkene. This is not an alkene, so we want to use a small base like methoxide, right, to create the more stable alkene right here. So we want to do E2 stuff here using a small strong base like that. But this alkene here is not this alkene. There's one more step we have to do here to convert that less stable alkene to the more stable alkene, which is isomerization, H2SO4 with heat. Right, so this was a pretty long one. The first step was E2 stuff. Second one, isomerization. Third step, hydroboration oxidation. Fourth step, oxidation. And then fifth step, Grignard reagent. If you want to do like the way Katya said with the ozonolysis, and you want to make this alkene right here, this is what you would have done. From this alcohol, we could convert that into a good leaving group with R SO2Cl, make that into a good leaving group, which is this. Wait. R SO2Cl. Yep, negative charge. And R right there. Okay. SO2Cl. Now this right here is a good leaving group. Let's do SN2 with NaBr to convert that good leaving group into Br. And I convert this into a Grignard reagent using Mg to create MgBr. And then if we want to go make an extra carbon, we do CH3Br to add a methyl group right there, right? Because this carbon here is going to attack that carbon, kick out the bromine, have that methyl group. And then from here, let's do... Actually, yeah, this one here is going to be a little bit weird, like halogenation Br2 with heat 118A, put a bromine at the more sub position right here, and then LDA to get that less stable alkene right there. So don't worry about this route here. Like if you wanted to go from what Katya said earlier, like where this came from ozonolysis, you would have to go through this whole route, which was not the intended route. Yeah, this right here would be low yield. That's good, Sharon, because in lab, when you put through a reactant through a lot of reactions, you're gonna lose a percentage of that original reactant after each reaction, right? So this is gonna be a very low yield. This would work, but it's so low yield that you're gonna lose points, especially for leave-ins. Helix might not care like how many steps you use. He might still give you full credit if it works. But leave-ins doesn't like that. Like when you use a lot of steps and you lose yield, right? Yeah. Okay. Let's see. Do you guys want to end off this session with one more synthesis problem, or are you guys fried right now? You guys are done. Number 3? Okay. Let's do number 3. Okay, number 3 right here. Let's move this line out of the way. Okay. We have an aldehyde here. Well, first let's do the same thing. Similarities, highlight that. Differences, circle that. Alkene, aldehyde. What functional group did this aldehyde come from? What do you guys say? Alcohol, yes. And okay, this is important here. Once we have this alcohol, right? Make sure to track that carbon-on-carbon, which is this pink carbon right here. Do not draw this right here. A lot of people would have drawn this as the alcohol, right? Where they substitute the whole aldehyde with that alcohol, but that's not right because we lost the carbon. That carbon-on-carbon right there, that pink carbon right there, right? Don't draw this right there. That's missing one carbon. Now, from this primary alcohol here, what reagent do we have to use specifically to get to that aldehyde from a primary alcohol? So NaBH4 is a reducing agent, right? So we don't want to reduce this. Jones is an oxidizing agent, and we do want to do oxidation. But Jones is a strong oxidizing agent. If we use Jones, this alcohol would become a carboxylic acid, but we don't want a carboxylic acid, right? We want to use a weaker oxidizing agent like PCC, right? When we had the secondary alcohol, it did not matter. You could use PCC or Jones. You always get the ketone. But this time we have a primary alcohol, and now it would matter what we use, depending on what we want. We want the aldehyde, so we use the weak oxidizing agent, PCC. Okay? Now, what do you guys notice about this alcohol? Is that the left subside or most subside? And if so, like what reaction adds the alcohol there at that side? Yep, left subside. What reaction creates alcohol at the left subside? So E2 Hoffman would create an alkene at the left subside, right? Because E2 reactions, elimination reactions, creates alkenes at the left subside, right? Hydroboration oxidation. BH3, THF, second step, H2O2, NaOH, water. And now, like Vladimir said, we see this less sub alkene. Now we want to do E2 Hoffman with LDA. And I said the bromine was right there, right? And then we want to make this less stable alkene. We use LDA like that. It wouldn't be E2 Hoffman because E2 Hoffman, we need a good leaving group like bromine. And E2 Hoffman creates the less stable alkene right here. Right. This reactant here is not a good leaving group. We're starting with an alkene and we want to create an alcohol on the less subcarbon. So that's going to do hydroboration oxidation. What if Br was here instead? What would be the reagent if Br was there instead of alcohol? HBr and ROR. Yes, this alkene to create that bromine and the less position is going to be HBr and ROR, which is going to create the bromine at the antimark side. It wouldn't be a small strong base because a small strong base would do E2 Zaitsev. And in E2 reactions, we need a good leaving group. There's no good leaving group here. So we can't do E2 reactions at all here. Right, so that's why we can't use a small strong base. Right. But we added alcohol on the less subcarbon, antimark carbon, which would be hydroboration oxidation. Yes, you do need to know Grignard reagents for this synthesis realm. Yeah, reagents reactions from Chem 118A, Grignard addition into an aldehyde or ketone. Yeah, and opening up epoxides in acidic versus basic additions, and carbonyl reduction with NaBH4 or alcohol oxidation with PCC. Okay. Now we see bromine here is on the less subcarbon of this alkene, right? And like we said, that would be HBr with ROR, which is going to add bromine on the less subcarbon antimark position. Right. So to summarize, first step, HBr with ROR. Second step, E2 Hoffman. Third step, hydroboration oxidation. Fourth step, PCC oxidation. Right. So this could get tricky because there's a lot of antimark reactions around. You guys would also have to know, like, for each reaction, what's the starting material, right? What's the reactant? Because E2 starting material is always a good leaving group, right? Not an alkene. We have an alkene here, we cannot do E2 at all. We need a good leaving group to do E2, either Zaitsev or Hoffman. And from this alkene right here, there's like multiple antimark reactions we could do. We could do hydroboration oxidation or HBr ROR or HSR ROR, right? Okay. You guys want to finish this session off with one last synthesis problem and then call it a night? One last one? Yes, let's do it. Okay, let me just create a random one. Let me think about this here. Oh no, Katya, I didn't have time to go over these questions, the textbook ones. Shoot. Let me think of one here. What reactions do I want you guys to use? Let's draw a fancy benzene ring there. Let's do... What do I want you guys to do here? Let's see. The yeah no, I'm not gonna become OChem professor. I'm just gonna like tutor OChem, but I am in chiropractic school though. Yeah. Right. Hopefully my iPad doesn't die before this. Okay. Mm. Nah, nah. Okay, box set. And once we have the box set, let's do. Let's do an alkene reaction from here, which is going to be. Oh, no, I don't think that's gonna show up. So let's not do that. Yeah, make it reasonable to Helix. Let's do. Um, mm, mm, mm. Yeah, let's do this. Coming from uh synthesis, you're gonna be pretty cooked if you don't remember the 118A reactions. But predicted product, mechanism, conceptual questions, explanation questions, you'll do fine. But synthesis columns, pretty cooked. You need the 118A reactions for 118A. Okay, let's do this. Yeah, there's like the major ones I would say for 118A. E2 for sure, 100% E2, Zaitsev and Hoffman. Alcohol dehydration for sure. Oxidation with PCC. Reduction with NaBH4. The Grignard reagents. And opening up epoxides in acidic versus basic conditions. Those 5 118A reactions are gonna be required, like to not be cooked. Yeah. Yeah, I think I put them. Yeah, I didn't put 118A reactions here, but I did do alcohol dehydration reaction here on the note card, but I didn't do E2 or Grignard in the note card, or oxidation or reduction. Hello? Where did my synthesis realm go? Oh my gosh. Let's hunt. Right here. Yeah. Okay, I'll give you guys some time to think about this by yourself. Hopefully we could do it with 2% battery left. Wait, what am I doing? I have a charger right here. Yes. You are right, Vladimir. I don't know what I'm thinking. Yes. Yes, I'm pushing my iPad to its limit. Yeah, gotta push your brains to the limit today. Past the limit. Mm-hmm. Let's do ozonolysis last step. Okay. Because you see that two carbonyls being cut open. So let's be ozonolysis ninjas and do ozonolysis in the last step. Let's say that was an alkene right there. Okay. Yes, my favorite too. Favorite alkene reaction. Should we take off the OH? Like from this last step or eventually somewhere backwards? Yeah, so you notice how the OH is at the more subcarbon right here? Right? Where did this alkene could have came from? This less stable alkene. If we go backwards. Mm-hmm. Hmm. Yes. In this case, I just realized that you could do a small base or bokeh base. Doesn't matter. I wanted you guys to use a bokeh base like LDA or tributoxide to make the Hoffman E2 alkene. Right? You're right, Katya. That was the intended route. But when I made this, I did not realize that you could do both, actually. Right? Because let's say that we have. Wait, actually, no, you can't do both. I'll show you guys why. So if it is OH right here, oh shoot, there's a problem here. Okay, so let's say there was a bromine right here. So the intended route is that I wanted you guys to make this less stable alkene using LDA. You could have used a small base as well, like ethoxide, right? Because this carbon here has no hydrogens. No hydrogens to take, right? So this is the only hydrogen we could take. Grab that hydrogen, make it a double bond there, kick out the leaving group, like that. But I just realized a problem here. When we try to do a strong base like that, something else would happen, right? There's a more acidic hydrogen, which is that alcohol hydrogen right there. So if we can still make this work though, but we're gonna do more 1:A reactions, which uh is going to protect this alcohol. Do you guys remember protecting alcohols in 1:A? Like let's say that alcohol was an ether, CH3. Yeah, what if we took the alcohol off before? Yeah. How can we do that? Yeah, let's say that this came from an ether, OCH3, and we did LDA. This is OCH. Oh no. Because deprotected, we have to use acid, but this alkene would get protonated as well. Let me remake this. So this is problem. So there's no problems here. No, there's no typos here. Let me remake this really quick. Oh my gosh. Yeah. If we do this right here, okay. Huh? What am I doing? Okay. Let's just do this one. Yes, this one here is doable. Yeah. Pose analysis. Cut. My brain is so mushy right now. Okay. And like we said, let's go do LDA. And this time we can only do LDA. We can't use a small base. We could use turbotoxide as well. We gotta do a Hoffman too, like that. Right. Yeah, smooth brain right now. Okay. Does this make sense so far, guys? Like how we went backwards to here? Like we did ozonolysis, alkene right there, and then we made this less stable alkene using E2 Hoffman LDA or turbotoxide from this bromine. Okay. Now I'll have you guys finish off the rest of the synthesis here. I'll give you guys some time to think about it. Oh my gosh, it's been 2.5 hours since we started. Could we take it off and put it on again? Take off the bromine and put on the bromine again. Oh my goodness, what am I doing? Let's put that methyl right there. Methyl right there. Methyl right there. Yes, let's do that. So if we see, okay, I wanted this to be the less subcarbon, but I didn't realize that they're both equally substituted. So let's say that we go backwards and say that was the less subcarbon right there. Sorry. I keep messing up on this synthesis problem. Right. So let's say that is the less subcarbon because my fault. I didn't add that methyl group right there. So if that was an alkene right there, what reaction adds a bromine to the less subcarbon right there? HBr would add bromine to the Markov position. So if we just do strictly HBr, bromine would be on the more sub position right there. Yes, roar. HBr, roar, heat. Okay, finally. Now we can go from here to here. Yes, that's good. Now, what reaction do we do from here to here? Do we do H2SO4 in heat? Do we do LDA? Do we do ethoxide? E2. Yes. E2 Zaitsev, because we want to make the more stable one. So let's do ethoxide. Right. Not alcohol dehydration, because we don't have an alcohol. Not LDA or turbotoxide, because we're not making this less stable alkene right there. We're making the more stable alkene from a small, strong base ethoxide. Like that. Yes. Nice. There was a problem here previously if I did not put that methyl group there, right? Because if that methyl group was not there, these two carbons would be equally substituted. So if you did HBr, you would actually get like a mixed product. You would get this Br, and you would get this Br right here. But I don't want that mixed product right there. We needed that methyl group right there to allow for this whole thing to go straight to here. Yeah. That's why that methyl group there was important, because I wanted to test on the anti-mark HBr roar thing here, right? So this synthesis problem, we did E2 Zaitsev, first step. Second step, radical addition with HBr, and then we did E2 Hoffman, and then we did ozonolysis. Yes. Okay. Walk you through this whole synthesis problem again. Okay, so we see that we have two carbonyls right here, and there's a cut right there. The reaction that makes that cut is ozonolysis, right? So to go backwards, we see that this was an alkene right here, where we cut that alkene using the ozonolysis reagents. First step O3, second step dimethyl sulfide. right? When we cut the alkene in half, we put oxygens in the middle to create these carbonyls right here. Okay, we see that this alkene here is the less stable alkene, less substituted alkene. So we're doing bulky base LDA or tributoxide here from this good leaving group right here, right? I don't want to do small base because I don't want this alkene right here. I want the less stable alkene, so I could cut the alkene in the right spot I want to get that final product. Okay, now we see that this is the bromine right here, that is on the less subcarbon, right? If there was an alkene right here, this is the less subcarbon of the alkene. And the reaction that adds bromine to the less subcarbon of the alkene is HBr, ROR, and heat, right? So that would add bromine to this carbon right here, the anti-bark carbon. Now to create this more sub-alkene from this haloalkane, we do E2 side stuff with a small, strong base. Like that, right? It took a while for me to form the synthesis problem because I had a different set of reactions in mind when I was making this, but it eventually like turned out to be this right here. Did that make sense? Like, did any step not make sense for you? Let's get. Okay. Why do we put bromine on 2C in 1 carbon? Yes, that's good. What, this bromine right here, why do we put it on this carbon and not this carbon right here? On the second. Oh, okay, I see. We put bromine on this carbon right here because we're comparing this carbon versus this carbon. We can only add bromines to either one of those carbons right there on the alkene, right? The more subcarbon or the less subcarbon. Yeah. And when we do HBr ROR, we have to add bromine to the less subcarbon, right? There's no alkene on that primary carbon right there. Right. Okay, okay. Let's skip. Yes. Should you draw the HNMR on your note card? I wouldn't, because Helix will provide you the HNMR chart and IR chart graphs here with the CNMR, HNMR shifts, and IR. But if you guys want a chart that can help you read IR, you could use this chart right here. Right, this chart is what I use all the time for IR. If you guys have it memorized already, then you guys don't have to write it down. Use ROR for less subcarbons aside from Hoffman. Yeah, ROR is to add bromine or SR to less subcarbons. Right, ROR is used to add bromine or SR to less subcarbons. Okay. The J values, yeah. Know that for sure for HNMR. Yes. I did go over a spectroscopy problem walkthrough for one of my previous office hour videos on YouTube, so you guys can watch that video to see my thought process, my 5-step process on spectroscopy problems. First step, DOU. Second step, IR. Third step, HNMR fragments. Fourth step, connect them and pray that you get the right one. And then fifth step, verify with all the information you're given. Yep. You gotta pray to the OChem gods, the spectroscopy gods, that you get it right, the specific structure. That's the most important part. You gotta pray to the OChem. You find synthesis harder than NMR? Oh my gosh. Dang. You did a lot of NMR practice then. That's good. That's good. Dang. Or yeah. I think it's because of the different reactions and different routes that you could do. Yeah. Like this is about to be like a 3-hour session. Let me end it here. Okay. That's good. How are you guys feeling so far? Are you guys feeling like better, or still like have a better idea of what to study? That's good. Yeah. A lot better. Need another Celsius? Oh my gosh. I'm praying for tomorrow. Yeah. It's good. Better, but still terrified. Yeah, of course. Look through the practice midterm that I gave you from winter 2023 for sure. That one like is Helix official questions, so know that, or know all of those questions for sure. Yeah, it's good. Yeah. Yeah, I'll send these notes on the Discord right after the session. And the recording too, right after the session. Yeah. Good night, guys. Yeah. Bye. Good night. Good night. See ya.